Welcome to the Explainer. So today we're diving into something where the stakes are quite frankly unimaginably high. You've got a floating production, storage, and offloading vessel, an FPSO, and you're basically living and working right on top of a massive hydrocarbon processing plant floating out in the middle of the ocean. A single error, a tiny miscalculation, it can be fatal. Out here, safety isn't just some corporate priority. It is literally the foundation of the engineering.
Which brings us to a really fundamental question. Why can't you just take a normal electric motor, like the one spinning away in your washing machine right now, and just plop it down on an FPSO process deck? Now, aside from the fact that doing your laundry on top of a crude oil tank is a spectacularly bad idea, there's a much more volatile reason.
The answer is as simple as it is terrifying. Every single electrical spark is a potential ignition source. And we are operating in an area where flammable gas is a very real, very constant threat. So to operate safely, we have to engineer what is basically an invisible shield against explosions. Okay, let's dive into our roadmap for today. We're going to cover 3 crucial layers. 1, mapping hazardous zones. 2, the power of ventilation. And 3, decoding ATEX equipment. All right, moving right along to Section 1, mapping hazardous zones. This is all about defining the unseen threat. If you were to look down at the layout of an FPSO process deck, you'd see this brilliant mapping of probability. Think of it as a giant dartboard of danger. We're mapping exactly where flammable gases might collect. You've got the accommodation block, where everyone sleeps and eats, tucked safely out of the way in what we call a safe area. But the rest of the ship? It's carved up into highly calculated specific zones. Let's break down the rules for these zones, which come straight from the IEC and European ATEX directives. Zone 0 is your constant danger. A flammable atmosphere is present continuously, or at least for long periods. Think inside cargo tanks or gas separators. Then you have Zone 1, which means danger is likely during normal operation, say within 1.5 meters of a tank vent. And finally, Zone 2. Here, a flammable atmosphere is unlikely, and if it does happen, it's only for a brief moment. The open process deck itself is typically Zone 2. Getting these classifications right is an absolute game changer because it dictates every single piece of equipment you're allowed to install there. But listen, we don't just sit around waiting for a spark to happen, right? We use gas detection systems as our invisible tripwires. The real danger point is when a gas release hits the lower explosive limit, or LEL. That's the lowest concentration where the gas will actually catch fire. But we don't wait for it to get to 100%. Our detectors trigger the alarms at just 20% of the LEL. By 50%, the emergency shutdown system automatically kicks in. It's a highly aggressive, proactive way to catch a leak way before things get critical. Moving on to Section 2, the power of ventilation. This is where we start physically manipulating air pressure. Now, what's really interesting here is the number 50, or, to be perfectly precise, 25 to 50 pascals. That is the exact amount of positive pressure you need to build an invisible wall. By pumping clean air into an enclosed, safe area, like an electrical switch room sitting right in the middle of a Zone 2 environment, we make the pressure inside slightly higher than the pressure outside. That slight positive push guarantees that explosive gases absolutely cannot force their way in through tiny cracks or gaps. If you trace the mechanics of this, it's pretty brilliant. Clean air is pulled in from a designated safe area, totally isolated from the hazard zones. It gets pumped into the room, monitored by gas detectors right at the air inlets, and then vented out through gas-tight flaps. And if those inlet detectors sense even a microscopic trace of gas, boom, they instantly slam the dampers shut and kill the fans. It acts as an incredibly effective physical barrier. And we don't just stop at pressurizing the air, we are continuously cycling it out. The strict standard dictates a minimum of 12 air changes per hour for these enclosed hazardous spaces. Why 12? Well, engineering calculations prove that 12 changes an hour is the exact sweet spot to rapidly dilute any small continuous gas leak back down to perfectly safe levels. The gas simply never gets a chance to accumulate. But here's where the engineering takes a complete 180. We just talked about positive pressure to keep gas out. Well, for a gas turbine enclosure, we actually use a negative 50 pascals of pressure. Why would we do that? Because the turbine itself might be the thing leaking the gas. By keeping that enclosure at a negative pressure relative to the surrounding room, we guarantee that if a leak happens, the gas gets sucked away and exhausted safely through spark-arrested outlets, rather than creeping out into the ship. It is literally manipulating the laws of physics to keep us safe. Okay, Section 3. Decoding ATEX equipment. This is the specialized physical armor of our shield. Every single piece of electrical equipment in these hazardous areas has to carry a strict certification, like ATEX or IECEX. So let's play detective for a second and crack the secret code you'll see stamped right on the machinery. XDIBT4. X is simple. It means explosion protection. D is the specific protection concept. Here it means flameproof. IB is the gas group. And T4 is the temperature class. Let's unpack exactly what those moving parts mean. First, the protection concepts. XD stands for flameproof. Now, this doesn't mean the box prevents an explosion from happening inside it. What it actually means is the enclosure is built so incredibly tough that if gas seeps in and an internal spark ignites it, the explosion is entirely contained. Any escaping flames are literally squeezed and quenched by narrow gaps before they can reach the outside air. But there's also XE, increased safety, which completely eliminates the spark from ever happening using superior insulation, perfect for zones 1 and 2. And then there's XI, intrinsic safety. This is the holy grail for zone 0. It operates on such incredibly low energy that a spark is physically impossible, even if you were to snap the wires in half. Next up in the code, the gas group. You see, gases are not created equal. They require totally different amounts of energy to ignite. Group 2A handles gases like propane, which actually takes a bit more energy to pop. 2B is for ethylene. But Group IC, that handles hydrogen and acetylene. Hydrogen has the absolute lowest ignition energy. I mean, a stiff breeze practically sets it off. So the takeaway here is if a piece of equipment is tough enough to be rated Group IC, it's safe to use with absolutely any gas group.
Finally, the T or temperature class. Because guess what? You don't even need a spark to trigger an explosion. Sometimes a hot surface is totally enough. The classes run from T1, which allows a max surface temp of 450 degrees Celsius, all the way down to T6, which stays super cool at 85 degrees. Our example code was T4, meaning it maxes out at 135 degrees. The absolutely crucial, non-negotiable rule here is this. The equipment's max temperature must always stay below the auto-ignition temperature of whatever gas is floating around it.
So let's bring the whole picture together. Engineering an FPSO process deck is way more than just bolting heavy machinery to a boat. It's weaving together 3 incredibly tight, interdependent safety nets. You mathematically classify your risk into zones 0, 1, and 2. Use highly precise air manipulation, positive and negative pressure, 12 air changes an hour, to herd the gas away from danger. And finally, you wrap your equipment in the strict physical armor of ATEX markings. That is how you build an invisible shield. But here is the ultimate engineering reality check. We have done literally everything mathematically and physically possible to prevent a gas explosion. But what happens if, despite every single layer of this invisible shield, a fire breaks out anyway? How on earth does an FPSO protect its crew and its hull from thousands of degrees of blazing heat? Well, that is exactly what we're going to uncover in Module 10 when we tear into passive fire resistance and deluge systems. You are definitely not going to want to miss it. See you then.